All right, let's talk hashing. First, a brief reminder about encryption. Encryption is a two-way process, and it converts a message using some sort of key. Whether you're using symmetric or asymmetric encryption is going to change the type of key that you use, but it's going to take some kind of message, use some kind of key, convert it into ciphertext, which looks kind of like what you see on the screen there in the middle, a whole bunch of gobbledygook, and then using that same key, if it's symmetric encryption, you're able to convert that gobbledygook back into the message. Hashing is different. Hashing is a one-way process, meaning there's no way to take a hash and convert it back to the original data. Unlike encryption, where the whole point is to be able to convert it back into the original message that was sent, with a hash, it's one way. And another aspect of hashes is that you can take any length of input, whether it's one sentence or the entire contents of Moby Dick, and it hashes to the same length output, which is part of why you're not able to take a hash and convert it back to the original data, because you're getting that same length output. It is fantastic for storing passwords. We'll talk about why. There's a link to a tool there so that you can see what hashing looks like. Let's look at some example hashes. MD5 is a common hash. It's not cryptographically secure, but it's a good hash. And it's a very popular hash for doing certain types of things. So here you see on the left is a list of inputs. Password 1, password 2, password with all lowercase. And each of the hashes for those MD5 hashes is the same length and completely different from each other. They're the same length, but the hash for password 1 looks nothing like the hash for password 2. And the hash for capitalized password looks nothing like the hash for lowercase password. And if I typed the entire contents of Moby Dick, put it in and hashed that, I would get an equal length hash on the outside that would, again, look nothing like the hash for password 1 or password 2 or password. So that's what hashes look like. So what are they used for? For one, they're used to ensure that a file has not changed or that your download wasn't tampered with. You might see, if you're downloading a Linux distribution or open source software, you might see somewhere on that page a link to hashes. And what you can do is when you complete the download, you run a hash on the download that you've completed and verify that the resulting value matches what you got from the website. And that makes sure that the file that you downloaded is the right file and that it wasn't tampered with or corrupted in any way. So you can also ensure that a file hasn't changed, meaning if I write up a document and cryptographically hash it, I can verify, again, by comparing the document, hashing the document again, I can verify that the document hasn't changed since it was hashed last time. This is used for digitally signing documents. When we talked about asymmetric encryption, we talked about digital signatures and how you use your private key to digitally sign a document. Well, part of doing that is creating a hash of the document, and that makes sure that the message hasn't changed. So you are signing it, verifying that you are the person who wrote it using your private key, and you're creating a hash of the document, verifying that the message hasn't changed, because on the receiving end, you're running that hash again, verifying that the message hasn't changed since it was sent and since it was signed. Again, also great for storing passwords, and hashes are also good for what's called proof of work. And proof of work is basically a way to prove that a computer has done some work to do something. And this is used for things like Bitcoin to prove that the computer's done work to compute some values. So that's one use. Things that you need to be careful with hashes. One thing is what's called collisions. And that's basically, so because any length of input, whether it's a sentence or Moby Dick, results in the same length of output, that results in a possibility for what's called collisions, meaning two different things could have the same hash. And creating collisions is a problem in hashing, because if two documents have the same hash, then you can't verify that those documents are the same. And that's bad. Because two different documents that have the same hash, they look the same hash-wise, but they obviously are not the same. So collisions are bad. And MD5 is, again, not cryptographically a good hash because it is vulnerable to collisions. Meaning it's possible to create two different documents, and it's reasonably computationally feasible, meaning you can do it in a reasonable amount of time, to create two documents that hash to the same value. So that's a problem. And that's bad because it inviolates the digital signatures, because two documents that have the same digital signature, it's bad. You don't want that. So collisions are bad. Pre-image resistance is how hard it is to find something that hashes to a particular value. So with collisions, you're trying to create two documents that hash to the same value. So I'm messing with document 1 a little bit and changing its hash. And then I'm messing with document 2 a little bit and changing its hash until I can get those two hashes to match. Now, pre-image resistance is saying I have document 1 and I can't change document 1. How hard is it for me to make document 2 hash to the same value as document 1? Or executable 2 to hash to the same value as executable 1? And that is a lot more difficult because you're not able to change both files. So it's a lot harder and a lot higher bar to clear. So collisions, or I guess it's a lower bar to clear. It's easier to have pre-image resistance than it is to prevent collisions. So MD5, again, it's a 128-bit hash, vulnerable to those collision attacks. So if you can mess with both documents, you can create two documents that have the same hash. SHA-1 stands for secure hashing algorithm, and that's a 160-bit hash, but it's also broken. It's basically got the same problems as MD5, so don't use either of those if you need cryptographically secure hashes, meaning you have to make absolutely sure that two documents are not the same document, or that are two documents that hash to the same value are absolutely positively the same document. SHA-3 is the newest standard for that, and it is, as far as we know, cryptographically good. So you can use SHA-3 to hash your documents and you're good to go there. Now, there's a whole other set of hashing algorithms that are deliberately slow, and bcrypt and scrypt are two examples of that. And the reason that a hashing algorithm is deliberately slow is that it slows down brute force attacks on passwords. And they are amazing, and they're used for password storage. And I keep teasing password storage, and we'll get there. And we'll get to the reason why hashes are used, or should be used, for password storage. The last thing, before we get to finally talking about passwords, is this thing called a rainbow table. And a rainbow table is basically, if you think of a dictionary attack is essentially a list of all the most popular passwords. And you're going to take that list and you're going to try all the most popular passwords before you move on to doing something like a brute force attack where you compute every possible password and try those. A dictionary attack takes the most popular passwords first. Well, a rainbow table is a way to store a dictionary attack on hashes. And you don't really need to, at this point, we're not going to talk a lot about exactly how a rainbow table works or how it's stored, but it is a way to simplify an attack on hashes. But to protect against rainbow table and dictionary attacks, we're going to do this little thing called salting. And now we're finally going to get to the actual use of hashes to store passwords. And the reason that we use hashes to store passwords is because passwords are super important. And the beauty of passwords is I don't actually have to know your password. If I run Gmail, I don't actually have to know my user's passwords. All I have to know is that they are able to enter the same password the second time that they entered the first time, or the 15th time that they come to the website, that they're entering the same password that they entered whenever they set up their account. That's all I need to know. I don't need to know that your password is password 1 or password 7 or 1, 2, 3, 4, 5, 6. I don't need to know any of that. All I need to know is that whatever you're typing now is the same thing you typed before. And That's exactly what hashes are good for. Hashes can verify that the input value at time 1 is the same as the input value at time 15, because the same input always results in the same output with hashing. So, but to store things in a database, we're going to use what's called a salt. Now, rainbow tables and dictionary attacks, remember, those are going to take a list of your most common passwords and the easiest to compute hashes, and we're going to automatically check for those when we compromise a database of passwords. So let's say you run Adobe and someone breaks in and steals all of your account usernames and passwords. What do they get? Well, if you've encrypted those, they get everything. If you've encrypted your usernames and passwords and they compromise your account, your database, if they can break that key, then they get all of your usernames and passwords. And that's bad. If we store them with what's called a salt, and this is what the database would actually look like. You would have a username, a salt, and a hashed password. And the way this works is that you would add the salt to the password that the user types. So in this case, username R. Schetzler, salt 2020G020, whatever. And then my password here is password. And I add the salt to the password. So I have 2020G blah 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 GAHNSD password. And then I hash that and store that value. And in this case, I'm using an MD5 hash, even though it's not a good secure one. It's an easy one to find websites that will do for you. And in this case, you'll notice 2020G blah 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 password computes to this hashed password of CC9B6F, etc. Well, Peyton Manning here, he uses the password as well. But he has the benefit of having a different salt. So ASDF, GNA, blah, 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 plus the password results in a completely different hash. So the benefits of the salt is that the same password, two users that have the same password don't have that same hash value in the password column of your database, which means that attackers who compromise that database have to compromise each account one at a time. They can't compromise the key or compromise one person who has the password of password and immediately know which other users, because they all have the same hash value in there. That salt generates a different hash value for each user. So that's going to slow attackers way down and add additional password security. So again, encryption is bad. It's terrible for password storage. It's good on top of having a salt, right? But and hashed passwords. But if you encrypt those plain text passwords and store them just as ciphertext and not as a hash, then basically by compromising that one key, and however they do it, by compromising that one key or one account, they get all of the passwords in that database, and that's bad. So again, a dictionary attack, you're going to try the most common passwords first. You might even have a list of the most common passwords. So as far as storing passwords best practices, again, do not store plain text passwords. Do not store encrypted passwords. You want to store the salted hash encrypted. So you would store that username and the salt in some value that you can get to. And then you would use some slow hashing algorithm. And again, the slow hashing prevents brute force attacks, because if I can compute a bunch of hashes really, really fast, then I'm going to just eventually try every possible password and see what works. By doing a slow hashing algorithm like bcrypt or scrypt, then that automatically slows that down. So if I can do, say, 1 million hashes per second, and I'm just making up numbers here. If I can do 1 million hashes per second, then I can check 1 million passwords per second. That's really fast. If I can only do 1 hash per second or 10 hashes per second, then you just slow down my ability to crack those passwords by a factor of 1 million or 100,000 or 10,000. And that has increased the amount of time that it will take for me to brute force or try every possible password on this account. So you store the hash. So you store username, salt, and that salted hash. So the login process, just to kind of give another overview of how this looks, when I create an account on a website, I'm going to set my password. The system would generate a salt and hash my password with the salt, and the database would store my username, the salt, and the hash. And then next time I log in, it's going to take the password that I enter, add the salt to the front of it, so salt plus password, slam those together, hash that, and just verify that that matches what I have in the database. And again, the system never has to know what password I typed in. All it has to do is compare the value of the hash on one end with the value of the hash on the other end. And so that way it never has to see my password. Basically, if you ever get an email from a company that says your password is blah, 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 unless that's a temporary one-time use password, that's really bad news, because that means that they have bad password security. And you don't want that. You should try to avoid working with that organization if at all possible, or telling them that they need to have better password security practices. And that's hashing.